I will introduce the next speaker, which is Professor Kevin Cowtan, who's based in York and teaches chemistry. And during their career, they have contributed hugely to methods development in crystallography. And as most people probably know, their fingerprints are all over the CCP4 software suite with programs such as density modification, Buccaneer, or libraries such as Clipper, just to mention a few. If you're solving a structure from scratch with CCP4, you will most likely at some stage be using software Kevin has written. Kevin is also contributing to cryo-EM modeling building software, as you may see from the bibliography. Lately, Kevin has also been prominent in the climate science debate, arguing for the fact that climate change is real and caused by humans. Among novice students in crystallography, one aha moment or epiphany typically happens when reading Kevin's explanation of Fourier transforms illustrated with a cat and a duck. I recall, I think it was last year at the Study Weekend talk, Kevin gave a talk, and while he was talking, actually a cat was walking in the background while he was speaking. And in my group, we were joking whether that was a Fourier cat or a real space cat. Anyway, Kevin has recently developed a method called shift field refinement, and that's the topic for today's talk. And with that, I would say over to you, Kevin. And just a comment about questions, please use Slack because it's easier to keep track of, and also you can continue the conversation and question and answers after Zoom has been shut down. So if you want to share your screen, Kevin. We can't hear you. Still no sound, but we can see your slides.
Right, my volume sometimes auto adjusts. Hopefully that's better.
Yeah.
Now share. Is that good?
That's fine, yes.
Brilliant, thank you. Okay, so I'll talk a little bit about shift field refinement, including a little bit about whether you should be interested in this or not. We'll come to that later, I guess. Refinement is a key step in the structure solution process, and obviously it can be difficult, especially after molecular replacement. But if it works, then molecular replacement is an incredibly easy approach to solving the phase problem. So if we can improve the refinement, we can make everyone's lives easier. So why is refinement hard? When we have significant shifts to loops or domains, then that can cause the refinement calculation to struggle. And inspired by the work of Tom Terwilliger on model morphing and also on Fourier model shifts from James Holton, I was wondering if there was something we could do with the calculation to address some of this. So how does refinement work? One of the fundamental insights comes from looking at the gradient map. This is a gradient in the y direction on this figure, up and down, and we see negative gradients below the atoms on that direction and positive gradients above, depending on which way you define the signs. So we're going uphill to get to the atomic peak and then downhill again as we leave the atomic peaks again when we calculate the gradient in this direction. And if this side chain needs to move in this direction, then we can see that in the difference map. We'll see the density where it should be up here and the density where it shouldn't be down here. And these two maps are correlated in this region. And that tells us that things in this region want to move in the positive y direction. And this is deeply embedded in the mathematics of how refinement works. So there are challenges here. Maps are noisy, gradient maps are noisier. And so as a result, if we say does the gradient map agree with the difference map? We can calculate that for each point where an atom is, and we'll get arrows going all over the place because of the noise in the gradient map and indeed in the difference map. A slightly better approach is to average over the volume of an atom, and that is slightly more sensible and actually has a sensible physical interpretation when you look at the mathematics of refinement as well. But in both cases, we're still tied to maps which at a detailed level can be quite noisy, especially when resolution is limited. So what do we do? Well, we introduce geometry restraints, and these pull against the density gradients to hold the model together. So the atoms get pulled in one direction by the density gradients and in another direction by the geometry restraints, and hopefully the combination of those two take groups of atoms in sensible directions. This can, of course, lead to slow convergence, although more sophisticated numerical methods can offset that. So the idea of shift field refinement was to try and get away from tying this to atomic parameters, because tying us to atomic parameters in some sense ties us to atomic resolution, even if we then mitigate that by geometry restraints. So the idea here was to try and get rid of the link to atoms entirely. And there is a stepping stone in between where we involve atoms in some sense. So instead of calculating shifts for individual atoms, what we'll do is look at big regions of the map, big spherical regions are what we use. And we ask, does the gradient map correlate with the difference map over a large region, not over a region of an atom? And that tells us whether these large spherical regions need to move, which that would be, depending on how the mathematics worked out, that might be hard work, that might be computationally very expensive, but actually it turns out that it's a very natural adaptation of the existing mathematical formulation of refinement. So a very slight tweak to the algorithm means that we're no longer looking for shifts to atoms, we're looking for shifts to big domains. Although we're not quite as specific as domains here, we're actually looking at, excuse me, spherical regions. So it's not quite the concept that we want, but it's useful. So we implemented this in an iterative approach, and it's kind of ad hoc. We ended up using 12 cycles of this shift field refinement, we call it, starting at 6 angstroms resolution and increasing gradually to 3 angstroms resolution. We don't go higher because that's a task for traditional refinement methods. So we do coordinate refinement, we don't refine B factors in this initial implementation, and then we go into RefMac and do conventional refinement to deal with any breaks in connectivity that have been introduced during this process. It tends to preserve geometry somewhat, but the distortions can build up over multiple cycles. One feature of the calculation is that it's very fast, and that's primarily because we can work at lower resolutions than conventional methods. The problem is if we do it for 12 cycles or more, we do begin to see chain breaks, even though we're moving big regions smoothly. If you do that enough times, then gradually things which are moving in different directions can move far enough apart to break connectivity. And in our initial version, we limited the calculation to 12 cycles to limit that to what RefMac could then restore. However, if we can restore connectivity or make sure it doesn't break in the first place, there's the potential for further improvements. So I implemented something that we call pseudo-regularization. So here was our initial model in this dark color, I guess is red. And then in light blue is what we got out of the first 12 cycles of shift field refinement. The thin black lines are actually the true structure. So what I do is take each 5 residue fragment in turn from the initial model, which has good connectivity, and move it to the corresponding 5 residues in the shifted model, which has poor connectivity. And then we do this for every overlapping 5 residue segment in turn, merge them all together, and we get a model that's now shifted, but has good connectivity and fairly good geometry. So if we do that, we can come up with an improved method. So we do our 12 cycles of coordinate refinement, 1 cycle of B-value refinement, which we can also do using shift fields, or we can do both together. And then we go through the pseudo-regularizer, and then we do the whole calculation 3 times because all of these steps are very fast. The pseudo-regularizer is almost instant. And then we go into refmac. And we compare this with the existing methods. So comparing R factors and R free with jelly body, the method as implemented was pretty similar to jelly body, although it was complementary. We saw some cases where jelly body was better and others where shift field was better. But the benefit of shift field was really that it was a lot faster. But there are benefits to using both. If we add the pseudo-regularizer and recycling, then we get about another 1% improvement in R factor and R free when averaged over about 450 test cases. Now, I don't want to oversell this, and I'll point out that Paul Bond has a different test set based on AlphaFold, and he finds that even with this improvement for that test set, jelly body is a bit better than shift field. So that these methods are still complementary. They still apply differently in different cases, and using both together probably has the biggest benefits, unless you're constrained by processing time. Paul has also done some other work. He's written a conventional regularizer to do normal bond length and angle restraints. And this has been done using the GEMI library plus some methods inherited from Coot. Now he tried this in the shift field calculation, and it didn't show any benefits in any way that we could see. However, this will be very useful because one of the things Marcin has done with the GEMI library is demonstrate that it can be compiled to WebAssembler, and therefore it will run in a web browser. And this is potentially one of the building blocks to build a future web Coot that will run in the web browser and can thus facilitate CCP4 Cloud. We have another implementation. This is quite a simple method computationally. So rather than everyone trying to use our code in their frameworks and dealing with making links between different frameworks, you should just re-implement it and use it wherever it's appropriate. So Scott Ho has done an implementation in Python in the Tempe framework for EM. So that's an additional way to use this. That's going to be available through CCP-EM. And the other thing we've done recently is implemented refinement of maps against either other maps or structure factors. So this is something that when I first presented this as an idea and showed a proof of concept, which must be nearly 10 years ago, I've just been distracted by other things rather than implementing it. This was something I showed as a proof of concept that we should be able to refine a map to match another map or to match a set of structure factors. Here is the blue map that we want to refine, and here is the true map, which in this test case, we didn't have phases for, we only had structure factors. And I showed that shift field refinement could shift the map to match the structure factors. So that's now implemented in the software in CSP4. And there's a potential speed improvement that we could get out of that by avoiding map calculation. So if you need even more performance, then you could discuss that with us. So far, performance hasn't been something that's come up, but there is more scope there. There are lots of potential applications of this, although none that we really have yet. So we're interested in ideas, if this fits a problem that you're interested in. So for example, we could now produce flexible NCS averaging, where we allow the different NCS copies which are averaging together to be flexible within any individual domain. Another possible application would be dealing with conformational variability in cryo-EM, where we have multiple different classes which differ by domain movements. We could combine different classes to further improve the number of particles contributing to any individual map, and therefore improve the resolution. And another possible application is this might be applicable to motion correction in EM images, in the original 2D images. So we would need another implementation for that in 2 dimensions. So that's the method. It's implemented in most CSP4I2 molecular replacement and model building pipelines. So actually, you don't really need to know about it, and perhaps not having to make a choice as to whether it is used is a good thing. So one of the things I worry about is whether the software that we use is determined by how convincing the speaker is, rather than how appropriate the software is to your particular problem. So in this case, that decision kind of goes away, because we're now increasingly testing everything against big test data sets of structures, and we're doing that at the pipeline level. So then the person who's building the pipeline can make a decision based on the test set of whether to incorporate a step in a particular case. It supplements a traditional refinement without impacting speed, and it's invisible to the user. So that does raise the question whether you need to know about it at all. I guess the reason for talking about it here is that you may have other applications for this kind of idea, which we might be able to help you with, or you may just be able to go and implement it yourself. So this has been worked on by Paul Bond, Scott Ho, Stephen Metcalf, and myself, and we've had funding from a series of BBSRC grants and from CSP4. And that's what I'd like to say. Thank you.
That was a very interesting talk, Kevin, and there's already lots of questions in the Slack channel. And I'll try and read up from the beginning. Yeah, so one question is, how does resolution relate to the sphere size in the shift?
Oh, yes. That's actually a very simple relationship. We tried, because the sphere size, the resolution determines the effective number of observations per cubic angstrom. So that's what resolution means. So if we want to retain a constant observation to parameter ratio, then the sphere size should scale linearly with the resolution. And in fact, having a sphere size of 4 or 5 times the resolution turns out to be about right. And that's just implemented in the program. You can override it, but normally you wouldn't need to.
Right. There's another question here. How does shift field compare with morph in Qt?
Morphing in Qt is kind of that I think that's the stepped refinement type calculation over a range of residues. So they have slightly different So rather than dealing with spherical regions, certainly in the Phoenix implementation, which I know better, that's dealing with ranges of residues. So the difference in behavior there, you would see, is that Tom Terwilliger's model morphing would be able to slide one chain against another, whereas that's something that shift field isn't going to handle well. But again, there is a difference in speed. So shift field addresses a particular kind of problem, which is these large domain shifts. It can, as you go to smaller spheres, deal with some more localized shifts, but not all of them. So it's part of a family of methods and should be seen as part of that family. So I think it will be complementary to COOT as well in that respect.
Right. There's one here from Clemens von Rijn. Regarding the limitation to 12 cycles, shouldn't refinement always be allowed to be run to convergence? Or is there no such concept of convergence for shift refinement? Stopping before chain breaks sounds a bit like there's some parameterization weighting not quite right.
So the fact that with no restraints at all, you will eventually get chain breaks from a smoothly morphing shift field is kind of inevitable. So that's not a parameterization issue. It's an issue that that the method is completely blind to the concept of connectivity. But you have identified something which is kind of fundamental, which is that there is a great deal of ad hocness in here. What we've done is something that comes very naturally from the mathematics of refinement, but has no crystallographic or structural biology meaning. And to get that to work in that particular context, we have ended up making some ad hoc decisions. Paul tried to firm that up by running to a minimum R factor at each resolution and then increasing the resolution. But we've never come up with anything that beats our initial ad hoc parameterizations. So that's frustrating, and I would love it to be more elegant, but whilst inelegant, it's elegant in the mathematical sense, inelegant in the implementation sense, but it's useful.
Right. So I'm just going to insert my own question here, because I was always thinking about, shouldn't the sphere size somehow be related to the LLG value for the model that you can compute from RefMax and say, and let that decide what is an appropriate sphere size for that particular problem?
Yes. So to some, our concept that there is a kind of concept of current resolution here, which comes from the quality of the phasing. So not the resolution limit of the data, but the limit of where your phases are meaningful. And that's kind of captured in the LLG value. I can't actually remember if our concept of, so yes, if we had a better, so ideally the weighting of phasing as a function of resolution should make that happen naturally. And so the fact that we incorporate a sigma A weighting stage should naturally degrade the resolution in such a way that happens automatically. Again, in practice, our experience is the ad hoc process works better than that. So I guess that suggests that we're not capturing all of the sources of error when we make our phase weighting terms.
Right, okay, I think we have to go to the next speaker, I'm afraid. And thank you very much for your talk, Kevin.